Okay, so we are going to start with the molecular orbital theory. So we need first to understand what the molecular orbital theory is. We can abbreviate that as MOT. So the molecular orbital theory states that atomic orbitals overlap to form molecular orbitals. Alright, so that is to form molecular orbitals. Now looking at the molecular orbital theory, we cannot go away from hybridization. So it's a very important thing for us to understand hybridization. So what does it mean that an atom has undergone hybridization? Because we are talking of atomic orbitals overlapping to form molecular orbitals. What are these atomic orbitals? What will be the molecular orbitals? How are they going to be formed? So now we need to understand hybridization. So a common example that we can give is carbon. So if we go on our periodic table, carbon has got an atomic number of 6. So the electron configuration for carbon is supposed to be 1s2, 2s2, and then 2p2. So that is the electron configuration. Do people have questions on this? Okay. So if we write the orbital diagram, the way you can see this is the increase in energy. This one is the lowest in energy, followed by that one, and then followed by that one. So an orbital diagram is going to show, first you've got the 1s, and then we go to the 2s, and then you've got the 2p. Now the 2p has got 3 suborbitals, so it is one orbital having 3 in it. So it is in that manner. So if we fill our electrons, which we have in this case, we have got 2 electrons in the 1s, so we're going to put them there. We've got 2 electrons in the 2s, we put them there. And then we've got 2 electrons in the 2p, so those we put them singly according to Bohr's principle, because you can't fill them together in the same orbital. So this is our carbon in ground state. So let's say this is at ground state. Ground state means it is just in a state where it is normal, it is not reacting, you are not supplying it with energy, you are not removing any energy from it. Now if it undergoes hybridization, so the first kind of hybridization we can talk about is sp3. So this kind of hybridization means we are combining one s orbital with p3 orbitals. Now what we need to get is, it is only electrons in the outermost shell which take part in a chemical reaction. So if we consider this, these two are coming from the second energy level. These two you can see in front is telling you second energy level. So it is only these 2 orbitals which are going to take part in a chemical reaction. The 1s can't take part because it is an inner orbital, and inner orbitals, in other orbitals which are in inner energy levels, cannot take part in a chemical reaction. So that's why the 1s doesn't take part in the chemical reaction. So what happens is, when carbon is reacting with 4 different things, okay, 4 other, it can be other atoms or molecules, as long as there are 4 other around it, it always undergoes sp3 hybridization. So what is going to happen is, this 2s orbital is going to come together with the 2p orbital. So now they are going to have the same energy. So looking at this, the way these two are, this one is higher in energy as compared to that one. But when they hybridize, they are going to become degenerate, meaning they are going to have the same energy. So it will be at that level where the hybridized one is going to come. Because we are talking about sp3, that means the 3 p orbitals we can see are going to combine with the 1 2s orbital that we can see, and so we are going to have the 4 of them are the same energy in that manner. So that is how they are going to become. So each of these you can see is what we are calling sp3. So this one is sp3, this one here is also sp3, that another one there we can see is sp3, and then the other one here is sp3. So each, just like these three here, we are all calling them the 2p orbital. All of these 4 here together are calling them the sp3 orbital. Okay, are there questions on that one? So noticing that if this happens, the 1s hasn't done anything. So the 1s will still remain the way it is as 1s. So now what is happening is the 1s, even the 2 electrons inside it, will remain the same. And then these 2 orbitals which have come together, since now they are degenerate, they are now at the same energy as we can see. So the 4 electrons, 1 there, 2 there, 3 and 4, those electrons are going to be equally distributed in the now formed hybrid orbital. So according to all those rules we learned, the Handy's rule, the Of-Bohr's principle, first we are going to fill the electrons singly in that manner. So those are the 4 electrons which are going to take up the space now of the hybrid orbital. They're just coming from these 2. And so when carbon wants to react with 4 other things, it undergoes sp3 hybridization. After doing that, those other 4 atoms that it is reacting will be bringing now each electron. So imagine it is reacting with 4 hydrogens, so to form CH4. So 4 hydrogens are going to come, and so each hydrogen brings an electron there, another hydrogen an electron there, another hydrogen an electron there, and also another hydrogen an electron there. So this is what happens in sp3 hybridization. So the molecular orbital diagram you are going to see. Okay, so we have got our carbon here, which has undergone sp3 hybridization. Remember there were the 4 of them. So we have got the first sp3, the second sp3 there, again the third sp3, the fourth sp3. So that is our central carbon here. Remember each of these have got 1 electron. So there is 1 electron there, there is 1 electron there, there is 1 electron here. Okay, please take note of the spins. There's 1 electron there. Spins mean the direction of the electron. So when we are talking about CH4, each hydrogen is going to come and attach to one of the hybrid orbitals. So one hydrogen is going to come here, another hydrogen is going to go there, another hydrogen comes here, and then another hydrogen comes there. And then each hydrogen brings on its electron. 1 electron there, 1 electron here, 1 electron there, and 1 electron there. Notice that the electrons in each orbital, one is pointing up, one is pointing down. They shouldn't point in the same direction. And so this is what we call the molecular orbital theory. Atomic orbitals have overlapped to form molecular orbitals. So now what you can see here is a combination. Okay, so the carbon, this orbital you can see here from the carbon is sp3, and then hydrogen, each of these are hydrogen atoms. Now hydrogen has got only 1 electron in the outermost shell, and so that electron occupies the 1s. So this orbital you can see here is the 1s orbital, which contains 1 electron, and so the bonds in methane are between the 1s orbital from the hydrogen and also the sp3 orbital from the carbon. So this is what happens in case of methane. Is there a question? Are there questions? Okay, if that were clear, let's try to look at sp2 hybridization. Now the one I'm from talking about is sp3 hybridization. sp3 hybridization. Now in this case, when it comes to methane, if they asked for the molecular geometry, the molecular geometry for methane is tetrahedral. So sp3 hybridization gives us a tetrahedral shape. So we have got a carbon, we've got an hydrogen, we've got an hydrogen, and then another hydrogen, and then another hydrogen. So this shape is called tetrahedral. So what is happening is something like that. So this is what we call a tetrahedral shape. That is why we are saying methane as a tetrahedral shape. So sp3 hybridization, take note, the molecular geometry is tetrahedral. Okay, let's look at sp2 hybridization. So for sp2 hybridization, same, our carbon, we are going to have first our carbon, which is at the ground state. A ground state, when carbon has not reacted with anything, it has got first the 1s having 2 electrons, and then it has got the 2s having also 2 electrons. Notice that they've got different spins. And then we've got the 2p, which has got 3 suborbitals having only 2 electrons. Yes, please. Yeah, they'll ask you to find the hybridization of the central atom. It's very much important. At times they might not ask you, but if they tell you to describe the bonding, for example, the bonding in a certain kind of element, these are some of the things that we need to talk about. You need to talk about the hybridization, you need to talk about the geometry, you need to talk about the magnetic properties as a description of the bonding. So leave out anything of such, then you have left out some marks. Okay, so we are going to talk more about that when we come even to VBT. So now when you're talking about sp2 hybridization, what is going to happen is only 2, as we can see it is sp2. That means we have got only 2 p orbitals coming together with 1s. Okay, I mean 1s, not this 1s we are seeing. I mean 1 orbital, s orbital. Okay, because we are saying the 1s doesn't take part in a chemical reaction, it is an inner orbital. So what is going to happen is during hybridization, only 2 from the top are going to react. And remember, the one which have been hybridized should be below this but above this. Now notice they'll be more nearer to 2p. Why are they going to be more nearer to 2p? Because 2p's are coming together with only 1s. So that's why they are going to be more nearer to 2p. So we are going to have, because we are talking of sp3, 1s is coming together with 2p's. So the hybrid orbitals will only be the 3 of them. So they'll just be 3. So 1p is going to remain on top there. It will bear the same energy like the original one. It's at the same energy, just that I can't draw it better, but it should bear the same energy than like the original one. And then this one, it is going to remain the way it is. It is going to be here. So this is the hybrid state. So this is the 1s, and then this is the sp2, and then this one which has remained is the p orbital. So what is going to happen is the electrons in the 1s are just the same, but these 4 electrons we can see here, they will be distributed equally. So 1 is going to be here, 1 is going to be there, 1 is going to be there, and then 1 is going to be there. So This is now the hybridized form of carbon. It is now ready to react with three different things. So when carbon wants to react with three different things, that is what happens. Now let's see when carbon reacts with three different things. Okay. Notice that, take note, there is one p orbital that hasn't reacted there. Okay. So for example, in C2H4, this is in ethane. So we have got carbon and then carbon reacting with hydrogen there, another hydrogen there, and then the other carbon also reacts with hydrogen and then hydrogen. Now carbon is supposed to have 4 bonds around it to be stable. Now notice that there are 2 electrons there, 2 electrons there, 2 electrons there. Only 6 electrons are present, and so that means the octet hasn't been balanced. So there exists a double bond there. So how does that double bond come? So we need to go to the molecular orbitals. Okay. So we have got our carbon, which has got first 3 hybrid orbitals. So the first orbital, it has got an orbital there, an sp3, it has got another sp2, and then another sp2, and then it has got one which was an hybridized. Remember, there was a p which was an hybridized, and the p orbital is like this. If we didn't know, it can be like that or like that depending on the plane. So it's like infinity. So the p orbital is going to be here. The one I've put in blue is p, starting from the top going to the down. And then we are going to have also another carbon, which has got first these orbitals which are hybridized, and then we have got the unhybridized orbital, which is the p, so it's going to be there. So these you can see I've drawn in green. That is the sp2. Even everything in green is sp2, so those are the hybrid orbitals. But when you're talking about sp2 hybridization, we had one orbital which was not hybridized. That is why you can see we have got this which I've drawn in red and also in blue. Those are the p's. So this is a p orbital from one carbon. This is also a p orbital from the other carbon. So each of these orbitals have got electrons in them. So there is an electron there, there is an electron here, there is an electron here. Remember, even the p orbital had one electron. Okay, even the other one, the p orbital is going to have an electron. And then even the hybridized ones are going to have electrons there. So there's an electron, there's also an electron. Even this side, the other one is going to, so there's also an electron. So one electron is coming from this carbon, the other electron is coming from the other carbon. So what is happening is we have got 2 hydrogen attaching to each carbon. So an hydrogen is going to come here, then another hydrogen is going to go there. Each of these hydrogens have brought together an electron there, an electron here. Notice they've got opposite spins. And then other 2 hydrogens are going to attach to the other carbon. And then they're going to come with electrons, an electron there, an electron there. So those are the hydrogens. So the bonds which we have here, there is a bond between sp2 of one carbon and also sp2 of another carbon. And then here, this is sp2 of one carbon and then S from an hydrogen. So these are the bonds present in here. We have got sp2 bond and then sp2 s bond, all the bonds which we can see here. Now where does the double bond come from? So these p orbitals you can see on top and down, they can overlap. So they can overlap in such a way that those electrons are able to move around. So they do, it's like they come in this manner, and then even this side they'll come in that way. So even from the other carbon, they'll come in that way, and also they'll go in that way. So this is the overlapping that happens. So these two electrons which we can see, these electrons here we can see, I don't know if we are able to see the color I'm using. So we have got this electron and this electron. Now they are able to move around. So those electrons can find themselves here. They've got opposite spins and they are able to move now in that fashion. They can move freely there. So that is what results to a double bond. So this bond you can see which is forming here is called a sigma bond. And then the bond which will be formed here is now what is going to result into a formation of a pi bond. A pi bond is what is called a double bond. So this is what happens in this case in our ethane. So we'll just show this to mean there is an overlap. So there is an overlap. Due to that overlap, that is why this double bond you can see here is formed. So what you need to know is that every single bond has one pi bond, and then a double bond has got one single bond and one pi bond. That is why you can see this is a pi bond formed between carbon and carbon, and then there is that is a sigma bond, not a pi bond. A sigma bond is simply a single bond. There's a single bond here, and then there's a pi bond. Notice that we only have one double bond in ethane. That's why there's only one sigma bond and one pi bond. And then a triple bond contains one sigma bond and two pi bonds. Okay, we are going to notice where that comes from. So this is sp2 hybridization. What of sp hybridization? Okay, let's try to look at sp hybridization. How does it work? And so when it comes to sp hybridization, what is going to happen is first we have got carbon in its ground state. So we have got this as the 1s, this as the 2s, even this as the 2p. I'm not even supposed to be showing the 1s because it is not involved in a chemical bonding. So when this undergoes sp hybridization, only one s is going to react with one p, and so the hybrid orbital is going to be on the very middle because it is 50-50. So after hybridization, only one s and one p is coming together, and then notice that two of these are going to remain. So the two of them are going to remain there. So this is a 2p, and then this one you can see formed here is the hybrid sp. So this one alone is sp, this one alone is sp, so there are two sps there. And then you have got the 1s which hasn't undergone any form of hybridization. So the electrons are going to be distributed also here. The 1s has got the electrons just like that, and then here the electrons are going to be distributed in that fashion. So each orbital has got an electron. Now let's see what happens in a chemical bond. How does it happen? So an example we can give is ethene C2H2. So this is, you have got a carbon bonded to a carbon and then a hydrogen and a hydrogen. Now notice that this carbon is only bonded to two things. That means we only have 4 electrons. It's not stable. So in ethene there is a triple bond between the carbon atoms. So what we are going to see is we have got a carbon, Remember, in sp, whenever carbon is reacting with two other things, this is our carbon, it is reacting, we call this as one thing and also this as one thing. It is reacting with two other things, and then the other carbon, also this carbon is reacting with one thing and also one thing there. So it's reacting with two things. Whenever it's reacting with two different things, it always undergoes sp hybridization. So what is happening here is we have got a carbon here. So sp hybridization means only two hybrid orbitals are present. We have got one here, we have got another one there, and then from the other carbon, let me show the other carbon here, we have got an hybrid orbital here and also another one. So these orbitals have drawn each sp. This is sp, this is sp, this one is sp, this one is also sp. Now notice just from seeing here, we have got a first bond is formed between sp and sp from each carbon. Okay, so let's take note of that. So remember, each of these orbitals have got one electron in them. So we have got one electron here, one electron here, and then there's also another electron from the other carbon, and then there is another electron. Now notice that they've reacted with each an hydrogen. So let me just try to show each hydrogen. So there is an hydrogen this side, there is an hydrogen the other side. So each hydrogen has brought an electron. They should have opposite spins. The other one, the electron is pointing up, the other one down. Okay, so this is what we have. But remember, in sp hybridization, 2p orbitals were unhybridized. So those two orbitals which were unhybridized, we are going to show them. So this will be the first p orbital which is unhybridized. Let me just draw it so that it looks much smarter. Okay, that's the first one. And then we have got another one that is not hybridized. That is another p. It may use maybe different colors. So this is a p orbital unhybridized. It has got one electron. Let me also show the other side. So this is also a p orbital which is unhybridized. It also has one electron. And then we have got the other one which is also not hybridized. Let me show it here. This also has got one electron. It is also a p orbital which was not hybridized. And then we have got another one there which is also not hybridized. Okay, so notice that we have got different ones which are not hybridized. Let me show this again in another color. I really want us to get a difference what is happening. Okay. All right. So what is going to happen is this: you are saying in blue are going to overlap. So this one is going to overlap with that other one, that side, and then even down they are going to overlap. So this overlapping is what forms a pi bond. So that is the first double bond that we have formed due to overlap. It's a pi bond. And then these yellow ones you can see also are going to overlap on top and down. So on top here they are going to overlap in that manner. Also down they are going to overlap. So the other overlapping is what forms a pi bond. Now this one, this bond which has been formed is not an overlap, it is actually a bond. So that bond forms a sigma bond. So this is what leads to a triple bond is in lithium. One double bond, another double bond, and then I mean one pi bond, another pi bond, and then a sigma bond. So whenever you see this, then that is a triple bond, because a triple bond contains one sigma. In other words, any bond contains one sigma bond, and then depending whether it is double, triple, or what, it is going to contain pi bonds. A single bond doesn't have any pi bond. A double bond only has one pi bond. A triple bond has got two pi bonds. If there is another bond maybe with 4, it's going to have 3 pi bonds. I don't know if that exists, but I don't know. I've never seen it. So that is the overlapping that occurs when you're talking about the molecular orbital theory. Atomic orbitals do overlap to form molecular orbitals. So this is what is happening. From this point, do we have questions? Before we talk about the molecular orbital theory and the molecular orbital diagram in nitrogen and also oxygen and other atoms. Okay, let's check the molecular orbital in other. Okay, so let's consider when you're talking about a nitrogen molecule, an oxygen molecule, a fluorine molecule, neon molecule, what will be the orbital diagrams for these atoms? And then using the molecular orbital diagrams, can we determine their magnetic properties? So let's start first with hydrogen, a very simple one. So now what we need to understand is this. When orbitals are reacting, those are atomic orbitals, AO, atomic orbitals. When atomic orbitals overlap, according to the molecular orbital theory, they form molecular orbitals. So when you have got this molecular orbital, let's call it the S, reacting with another molecular orbital, let's also call it S. Now the kind of molecular orbitals, these are atomic orbitals which are reacting. The kind of molecular orbitals which are going to be formed are 2. So what will be formed? We have got a molecular orbital which will be formed which is higher in energy, and the molecular orbital which will be formed that is lower in energy. So nature always wants to have minimum amount of energy. So notice that these 2 orbitals are higher in energy than this one which I'm trying to draw here. So this one which will be down will be supporting a bond. Whenever you are trying to lower energy in a bond, then that bond is favorable. So these are what we call bonding molecular, because now we have formed a molecule. Bonding molecular orbitals. Now the one which are on top here, these don't support a bond. Why? Because they are using up a lot of energy even than single atoms. Now get this. You would rather be in a state that is making you to lose little energy than in a state that is giving you pressure. For example, if you've got a heartbreak or something, you are always spending a lot of energy on emotions and thinking and such a thing, and so you are not stable. So you always want to cool back. So cooling back, you are going to be stable. Okay, so that is why atoms would rather achieve a state where there is minimum energy. In this case, bonding molecular orbital has got more minimum energy than when the atoms are alone. But if you consider this other one which is on top, this is the anti-bonding. So this one favors atoms being alone instead of them being bonded. This is what we call the anti-bonding molecular orbital. Okay, so that is called the anti-bonding molecular orbital. So this one is taking in a lot of energy, just a lot of energy. So you'd rather not be there. So it is just as simple as this. Why is it that these are together? They are together but they are not bonded. Even these are together but they are not bonded. It's like this. Imagine you have got a friend of this friend who you love very much. So you have got different houses. You are in a different house, the friend is also in a different house. So in that way, you are not troubling each other very much. You are at peace. Now, immediately you come to that your friend, maybe say they are your, I don't know, any kind of friendship, I don't know, you can mention. Whenever you are together, it's like you're always arguing. So in other words, you are spending too much energy. So it was better you stay away from each other. But imagine you have got also this friend, when you are away from each other, it's like you are spending too much maybe on talk time talking to each other, but immediately you come together, you have got little to spend. So you'd rather spend a lot of time than when you are away from each other. So this is what is happening. The anti-bonding molecular orbitals always takes in a lot of energy, and so we would rather not be there. Okay, so anti-bonding molecular orbitals, we call them, so you are going to see a star on top, but these we don't put any star. You are going to understand what is happening. So for example, let's give an example of our hydrogen molecule. Now hydrogen molecule comes from two hydrogen atoms. Each hydrogen has got an electron configuration of 1s1. It has got only one orbital. So that means we've got one orbital coming from one oxygen, I mean from one hydrogen, 1s, and then the other one, the 1s coming from the other hydrogen. So each of these are hydrogens. So what is going to happen is, these are atomic orbitals that side, and then another atomic orbital this side. So when they come together, there will be a molecular orbital which will be on top, and then a molecular orbital which is down. So this is what we have. Okay, sorry for that. Okay. Alright, so this is what we have formed. So remember, each hydrogen has got one electron in the orbital. One electron there, one electron here. So now what happens is, this orbital which has been formed, which is lower in energy, because it's coming from S and S, it will be also called an S orbital. Okay, it is also an S orbital. But because it is an orbital which is supporting bonding, an orbital which supports bonding will be just called the sigma S. Why are we calling it sigma S? That is because it forms a single bond. Okay, whenever you see only one orbital, just one orbital like this, it forms a single bond. Like one electron is going to come from one atom, another electron from one atom, and so on, a single bond is going to be formed. Because they are coming from the 1s, so we are going to call it a sigma 1s. And then the one which is higher in energy is also a sigma 1s, but because it is higher in energy, it doesn't support bonding, we put a star there. So it is a sigma star 1s. Sigma star 1s. So what you do is, you are going to get this electron and this electron. So you have got two electrons present. So those two electrons present, you are going to use the Pauli's exclusion principle, the off-Bohr's principle, and the Handy's rule to fill this orbital which we have here. Okay. So what we are going to do is, remember we have got two electrons which are present. So we are going to go on and fill. You first fill the lowest available energy orbital before you go to the higher orbital. So that means the two electrons which are present, we are first going to fill them in here. So that means all the two electrons have been taken up just by the sigma 1s orbital. So the sigma star 1s is not going to take up any electron because we don't have any electron which is there. Because trust me, you cannot opt to go and occupy this orbital. Even if it were you, you cannot opt to go to something that will give you pressure, if there is even something that is giving you peace. So that is why electrons are taking up the lower orbital. Okay, so this will be the molecular orbital for our hydrogen molecule. Now from this molecular orbital diagram, we can calculate what we call the bond order. So bond order is simply have bonding electrons minus anti-bonding. Let me just write AB. That is meaning anti-bonding electrons. So that is the formula that we use. So that will give us half. Now bonding electrons are those electrons which are in orbitals which don't have a star. So this which we have here is a molecular orbital which has been formed by the overlap of two atomic orbitals. Please just be free to ask when you are not fine. Alright. So we are going to go on. So we are saying the bonding atomic orbitals, bonding molecular orbitals, those without a star, we have got two electrons there. So we are going to put our 2. So we have got 1/2 and then 2 minus anti-bonding. In the anti-bonding where there is a star, do we have any electron? No. So it's 0 there. So 2 minus 0 divided by 2 will give us a 1. So this is the bond order. I didn't even complete the word. That is bond order for our hydrogen. So what bond order tells you is, it tells you is it possible to form a bond between two hydrogen atoms or it is not possible. If it is possible, how many bonds can be formed? So this is telling us that a bond is possible and only one bond is going to be formed. So that is why the bond order is 1. Now, if they ask us to determine the magnetic properties, is hydrogen molecule able to be attracted by magnetism or not? Magnetic properties we talk about, is it paramagnetic or diamagnetic? So you look at the molecular orbitals, those orbitals which have been filled, as you can see, one of these orbitals which has been filled, is it all fully occupied or it has only been occupied by a single electron? So it has been occupied fully. So there are 2 electrons. 2 means di. So that means the kind of magnetism here is diamagnetic. Okay. Diamagnetic. So this is a kind of magnetism in our hydrogen molecule. The bond order is 1 and then the magnetic property it is diamagnetic. Now bond order is related to the stability of a molecule. Bond order is related to the stability of a molecule. So for this case, after saying that, let's determine which one is going to be more stable. Is it hydrogen molecule or hydrogen molecule plus or hydrogen molecule minus? Which one is going to be more stable? So I've got H2 and then H2 plus and then H2 minus. Let's determine which one is going to be more stable. So for us to determine which one is more stable, we need to use the molecular orbitals. So the first thing is, let's start with our hydrogen, just the hydrogen molecule. So we have got first one orbital here, one orbital. Okay, let me write them well so that they are going to all be written. So we have got these 2 and then we are going to have an anti-bonding orbital on top and then a bonding orbital down. Okay, let me just put that to represent they've been formed from those. So this is a 1s, this is a 1s. So this is hydrogen molecule. And then let me go to the other one. I just draw the 3 of them. So this is the 1s, this is also the 1s. So this will be my hydrogen 2 plus. Please, these should be at the same energy. This one should be higher in energy. If you put it on this line, you are automatically wrong before even doing anything. So they should be on the same these two same energy. That one should be higher, this one should be lower. Draw anything parallel to that at your own risk. Okay, so this will be my hydrogen 2 minus. This is still 1s. This is also 1s. Now we start with the first one. Hydrogen molecule already said that there is one electron here, one electron here. The orbital which is down is a sigma 1s. The one on top is a sigma star 1s. So the electrons, we found that they only occupy the lower one. And then if we go to the second one, if we have a plus, plus means we've lost an electron. So that means only one of these atomic orbitals are going to bring out their electron. One of them have lost an electron. That means we're only going to have one electron in what has been formed. Because we have lost an electron, that is the meaning of a plus. And then when we come to the third one, it means one of the orbitals have gained an electron. So we're going to have an electron there, an electron here. One of these have got an extra electron in that manner. So we have got 3 electrons present. So those 3 electrons present, we are going to fill them now in our molecular orbital. So 2 are going to occupy this. So the other one, we don't have a choice but to throw it there. I don't want to give another example. Hope we've already understood what is happening. So this is a sigma 1s. This is a sigma star 1s. And then this is a sigma 1s. This is a sigma star 1s. Now we need to calculate the bond order for all of these which we can see here to determine the stability. So let's start with the first one. Bond order, I already wrote the formula. It's given by half. Bonding electrons. So these electrons here are what we call bonding electrons. So there are the 2 of them. Anti-bonding, where there is a star, we don't have any electron. So that is -0. So the bond order here is 1. And then if we go to the second one, bond order is going to be given by half. Bonding electrons, we can see we only have 1 electron here. And then we don't have any electron in there, so there is a 0. So that is going to give us what? 0.5. And then if we go to the last one, bond order is going to be given by half. Bonding electrons, as we can see, we have got 2 there. Anti-bonding electrons, we have got 1 where there is a star. So that is going to give us 2 minus 1 is a 1. That will give us 0.5. So the higher the bond order, the more the stability. So this is telling us that hydrogen molecule is the most stable as compared to the 2 hydrogen molecule ions. Now, how do we determine, because both of these have got the same bond order, how do we determine which one is more stable than the other? So we have already seen H2 is the most stable. Now let's determine the 2. So if the 2 have got the same bond order, what you need to go to look at is now the anti-bonding electron. Okay, the anti-bonding orbital. Does it have any electron or not? Get it like this. Some of us, even if we get a 2%, we go home. There will be no one to trouble us. We are going to be at peace. Others, when they get a 40%, they go home. They'll be like, why are you getting that 40%? They'll be in pressure to study so much hard. So this is what is happening. This one, though it has got this bond, though it has failed the test, but it doesn't have anything to trouble it. That is why it is much stable. But this one, it has failed, but there are people troubling it. Get it in that form. There are people troubling it, so it is not stable. So that is why H2 plus is more stable than H2 minus. So the stability here is H2 is more stable than H2 plus, and then H2 plus is more stable than H2 minus. So that is the stability when it comes to these. Are there questions? Are there questions? Okay, that's nice. So let's look now at the molecular orbital diagram for hydrogen. Hydrogen, we've already looked at it, so we go to oxygen, neon, and fluorine. Now, the badness, I don't know if it's the badness or what, you need to know, and no one will tell you. Fluorine gas, neon gas, these are molecules, sorry, not gases. Fluorine molecule, neon molecule, and oxygen molecule, they've got the same molecular orbital. Everything that you are not seeing here, they've got another one, such as chlorine 2, nitrogen 2. What can we talk about again? Any other thing that you cannot see from these, they've got the same molecular orbital. In other words, all those atoms which form that you can draw, they've got another molecular orbital diagram. Chlorine 2, N2, I don't know others you can mention from the periodic table, those which can form molecules. Okay. So now let's try to draw. We see what is happening. I'm going to start with neon. Neon 2. So the first thing before you write the diagram for neon 2 is you need to know the electron configuration for neon. So checking on the periodic table, neon has got 10 electrons. So that means the electron configuration is 1s2, 2s2, and then 2p6. That is the electron configuration. Now remember, I already stated it. Only electrons in the outermost shell take part in a chemical reaction. So it is only the 2s, okay? The 2s and the 2p, those are the electrons in the outermost shell. The 1s doesn't take part in a chemical reaction. How do I know which ones are in the outermost shell? You look at the number in front. This is meaning second shell, because you know that neon only has 2 shells. And so those are the ones which are going to take part in a chemical reaction. So we are first having 2s, another 2s there. Okay, this is a 2s from one neon. This is the 2s from the other neon. When these come together, they are going to form the one which is higher in energy, and also another one which is lower in energy, in that manner. And then this is the 2s I've drawn. Remember, it also has a 2p, so we need to draw a 2p. Now notice that the 2p has got 3 suborbitals. So those are the suborbitals we have. And then even there, so this is the 2p from the other neon, and then this one is the 2p from the other neon. Now, according to the molecular orbital theory, atomic orbitals which do overlap are equal to the molecular orbitals being formed. So look at here, we've got 3 atomic orbitals, 3 atomic orbitals. When they do overlap, how many are going to be formed? 6 atomic orbitals. So since atomic orbitals are present, 6 molecular orbitals have to be formed. Now for this one, for neon molecule, oxygen molecule, and also fluorine molecule, they've got the same molecular orbital. So this one I'm drawing is a general for all of them. So where first you have got so this is what is there in all those 3 that I've shown. I don't know if that is better, good enough. Okay, so this is what we have. This is a general molecular orbital diagram for these 3 which I've drawn here. So we are going to fill in our electrons. The 2s has got 2 electrons, so this 2s this side has got 2 electrons. Yes, go on, sir.
Why have you written like the single particle and the double orbital? Why are you like three of them?
Okay, that's a nice question. Alright, let me just put the electrons which we can see and then I talk about that. So these are the 2 electrons we can see there. And then if we go to the 2p, each p has got 6. So 1, 2, 3, 4, 5, 6. And then this one also 1, 2, 3, 4, 5, 6. Okay. Now going back to the question asked, remember when we are talking about p orbitals, we have got px, py, and pz. So these are the ones we can see: px, py, pz. But in a chemical reaction, two of these have got the same energy while the other one has got energy different. So that is why these two have split. Okay, two of these have got the same energy, that's why they're always together. But one of them is going to have a different energy, and that energy can either be higher or lower. Just like for this one here, the energy for one is higher, but down here the energy for one is lower. So the badness is there's no better clear technique that we can use. We say, okay, this is the procedure that you need to understand for you to find the molecular orbital diagram. If you follow a lot of people, they'll just tell you. The badness is you need to master. So as you see now, it is just coming from the head. I don't have an option but to know it in the head. And so, dear friends, let it be also in your head. So this is how it's going to be. Now if you notice, we said 3 are here, 3 are here. 6 molecular orbital, 6 atomic orbitals are present. So 6 molecular orbitals have to be formed. As you can see, 1 there, 2 there, 3 there, 4. Even my counting is bad. So we have got 1 here, and then 2 are there, so that will make 3. And then 5, 6. So you can see that the atomic orbitals which were present, reacting, or combining, or overlapping are equal to the molecular orbitals which have been now formed. Now we need to name these molecular orbitals which have been formed. Starting with the first down one here, it is because it is only one orbital is always a sigma. So this is sigma, but because it's coming from the 2s, that will be called sigma 2s. Notice that this one is single, but it is higher in energy. It will still be a sigma, but we are going to put a star and then 2s because it's coming from the 2s. And then come here. I've written this line to divide those lower in energy from those higher in energy. Those higher in energy always put a star. So notice that this one is only single, but it is lower in energy, so it will be a what? A sigma. It is coming from the 2p, so it will be a sigma 2p. And then these are lower in energy, but there are the two of them. Whenever there are the two of them, it is a pi. So it will be a pi. It is coming from the 2p, so it will be called a pi 2p. This one is higher in energy, but there are the two of them, so it will be called a pi star. There are the two of them, that's why calling pi. The star is coming because they are higher in energy than these two which are making them up. So they are coming from the 2p, so it will be a pi star 2p. This one is a single one, so it will be called a sigma. And then it is higher in energy, we are going to put a star. It is formed from the 2p overlap, so we are going to put a 2p. So it is a sigma star 2p. Are we fine? And then we start filling now our electrons. So if we consider the 2s, they have got 2 electrons there, 2 electrons there, making 4 electrons. So those 4 electrons, we are going to fill them in these 2 orbitals which they are forming. So starting with the lower orbital, fill it 1, 2, 3, 4. So we have fully filled them. Fine. So we are done. All the 4 are done. Now if we go to the 2p and then 2p, there are 6 electrons, there are 6 electrons, giving us a total of 12 electrons. So we are going to fill those 12 electrons starting with the lower energy, the one which is at the lowest energy. So remember there are 12 electrons present. So we have got 1, 2, 3, 4. Notice that these which I'm filling here, which are together, I'm first filling them singly before filling them doubly. We need to understand the Hofbauer's principle, Handy's rule. So I'll fill them 4 and then I come 5, 6 and then I go higher 7, 8, 9, 10, 11, 12. All the electrons have been filled up and all the orbitals have been filled up. Now let's determine the bond order. So the bond order is equal to half bonding electrons. Bonding electrons, just get electrons which are in orbitals which don't have a star. So we can see there's no star here, there's no star there, there's no star there. So we have got 2, 4, 6, 8. So we have got 8 electrons which are bonding. So bond order is equal to half bonding electrons which are 8 and then minus, did I say 6? So they're supposed to be 8. Let's go to those which are anti-bonding, those which have got a star. So we have got a star here, we've got a star there, and then we've got a star there. Let's count them. 2, 4, 6, 8. So we are going to put 8 there. So we have got 8 minus 8, which is a 0. 0 times half is still a 0. So what this bond order is telling us is it is not possible to have neon molecule. This can't be. Inert gases, group 8 elements cannot form a molecule. That is because they are already stable, they can't form a molecule. So neon likes being single. It would rather just be alone, because whenever it is with something else, it will be in trouble. So neon doesn't form a bond. Okay. And then if we want to determine the magnetic properties, notice that all the orbitals which have been formed here are completely filled up. And so this is telling us that neon has got a diamagnetic property. Okay, it is diamagnetic. Is there a question? I got just to look on at oxygen as the other example on this kind of diagram. Remember, I've shown 3. We have got neon, oxygen, and fluorine. And then the fluorine, we are going to try it out at your own time. Even others, we are going to practice at your own time. Alright, so let me write for oxygen. So oxygen has got 8 electrons. So the electron configuration is 1s2, 2s2, and then 2p4. So again, just get those electrons are in the outermost shell. So the 2s2 and then the 2p4, those are the only ones which are going to use. Okay, so I want to draw our oxygen molecule O2. So the first thing we are going to draw are the other orbitals, the atomic orbitals from each oxygen. We have got from this oxygen and then from the other oxygen. Please, as you can see, these are the same energy. Should you draw anything else, they will be happy. So this is the 2s, this is also the 2s. They are the same energy. So the one which will be formed now after this overlap, we are going to have one higher in energy and then another one lower in energy. Okay, and then we go to the 2p. Remember, p has got 3 other orbitals. So we have got here, and also from the other auction. Remember, all 2 auctions are coming together. Okay, we have got 2p. Even the other one I've drawn that side is a 2p. So same orbit, same also, you are going to have first a double one which is like this, and then a single one which is going to be there, and then you are going to have a double one in that fashion, and then a single one on top. I don't think this is cumbersome to know. Just know that these two which are double will be near to each other, and then the single ones will be outside. For oxygen, fluorine, and neon, I haven't mentioned anything else, unless there is anything else which I haven't come across. You can still discover that it is not, knowledge is not limited. Okay, so now we can put our electrons. Remember, this one had 2 electrons. From the electron configuration it was 2s2 and then 2p4. That means we have 4 electrons here, 1 2 3 and then 4 there. Even the other side, 1 2 3 and then 4 there. So before I even fill them up, let's label the orbitals we have. This one is lower in energy, so it will be a sigma. It's coming from 2s, so it will be a sigma 2s. This one is higher in energy, so it will be sigma star because it's a single one. It's coming from the 2s, it will be 2s. And then this one which is here, it is lower in energy and it is only one, so it will be sigma, but it's coming from 2p, so it will be sigma 2p. This one, there are the 2 of them, so it will be a pi. It is coming from the 2p, 2p. This one, there are the 2 of them, but it's high in energy, so it will be pi star, is coming from 2p. Then this one, it is 1, but is higher in energy, to be sigma star 2p. Now let's fill the electrons which are present. Starting with this, we have got 4 electrons present, so those 4 electrons are going to fill them. So 1 2 3 4. Okay, done. And then here we have got 4 electrons, 4 electrons, so 8 electrons present, and then we fill them. So we are going to say 1 2 3 4 5 6 7 8. So this will be the molecular orbital for the oxygen molecule. Notice that here each electron is in a single orbital. They are not in the same. So I again encourage you, please revisit the Pauli's exclusion principle, the Handy's rule, the off-Bohr's principle. Know how to state them. Alright, now let's determine the bond order. The bond order is going to be given by half. Bonding electrons, where there is no star, we have got 1 there, we've got there, and then we've got there. So if we count them, 2 4 6 and then 8, so there are the 8 of them, so that is 8. And then minus anti-bonding, where there is a star, we have got 2 there and then 4 there, so there are only 4. So 8 minus 4, okay, 8 minus 4 is a 4, and then half multiplied by that 4 is going to give us a 2. So this is telling us there is a bond which exists in oxygen molecule, and that bond is a double bond. That's why you can see a 2. So there is O double bond O. So this is how oxygen is. In case they ask you to draw the Lewis structure for oxygen, this is what is going to happen, and then just put the lone pairs. So that is the Lewis structure for oxygen. Anyway, we're not talking about Lewis structures. So this is our oxygen. I'm not going to remove this. Okay, now let's determine the magnetic property for oxygen molecule. Notice that this is double, this is double, this is double, that is double, that is double, but these are single. So because we have got two orbitals which are singly occupied, then the magnetic property is paramagnetic. So that is paramagnetic. Okay, so that will be it. It's paramagnetic. Alright, so let me look at nitrogen. So remember I said anything else apart from, so this kind of orbital diagram I've shown here is for neon 2, oxygen 2, and then fluorine 2. Anything else like nitrogen is going to change. So let me draw for nitrogen 2, and then the other ones you can also try them out. So if we check nitrogen, nitrogen has got 7 electrons in the outermost shell. So the electron configuration is going to be, I just want electrons in the, okay, it will be 1s2, 2s2, and then 2p3. This will be the electron configuration for each hydrogen. So I'm just showing the, this is the 2s, this is the 2s, and then lower in energy and also higher in energy. And then you are going to have the p this side. We are also going to have the p that side. Okay, so this is the 2s, this is the 2s, and then this is our 2p, this is also our 2p this side. So now what happens is for this, these two you can see there, they are going to swap. That is the only difference. Okay, so the one which is going to be down is where there are 2, and then this other one is going to be alone. Please, it's just that my drawing, my board seems to be small. Otherwise this one should never be straight with these other ones. It will be wrong. It shouldn't be. That's why I'm always trying by all means to put it down. So these two swap. That is the only difference. And then the ones which are on top, they just maintain their positions. So we have got like that. And then the other one is just the same in that manner. Okay. So that will be the diagram then. So we can put in our electrons now. We saw that the 2s had 2 electrons even this side. And then the 2p had only 3 electrons. So 1, 2, 3. And then 1 there, 2 there, and then 3 there. So let's first label the molecular orbitals. This is a sigma 2s. This is a sigma star 2s. This is a pi 2p. This is a sigma 2p. This is a pi star 2p because it's high in energy. The sigma star 2p. Okay, now we fill in our electrons. Notice that there are 4 electrons present. So we are going to fill in those 4. 1, 2, 3, 4. And then here we've got 3 this side, 3 that side, making 6 electrons. So we have got 1, 2, 3, 4 there, 5, 6. Okay. So that is all. The 6 you filled up. So this is our nitrogen molecule. Let's determine the bond order. So the bond order is going to be equal to half. Bonding electrons, we have got 2, 4, 6, 8. So there are 8 bonding electrons, and then the anti-bonding, where there is a star, we only have 2 there. So 8 minus 2 is a 6. 6 divided by 3 is a 3. So this is telling us that a bond in nitrogen is possible, and it is a triple bond, as you can see by the bond order. Now, looking at our nitrogen, you can see that all the orbitals have got 2 electrons in them. So nitrogen molecule is a diamagnetic molecule. Okay, it's a diamagnetic molecule. Alright, are there questions? Are there questions? Alright, so the quietness is telling me it is so clearly understood. And the lesson ends here today.